So Rob, I'm going to start, but you should get started. Okay. Starts the same time. So welcome everybody to Sam's M exam. Sam has been at Cornell for quite some time, so I'm going to give a very brief introduction. So he did his undergrad here, and then during that time we met because he took all of my classes, and despite that, still wanted to work with me, which I think is like credit right there that he survived them and didn't run away. So he joined the lab as an undergrad and then stayed on for his MS with our lab, and has really been a very special MS student. I have to say, most people come into a project and they flourish within that project, and Sam was much more so. He had ideas, and he really kind of saw where he wanted to go. He saw where he wanted to go for his career, and he is very good at presenting those ideas and kind of figuring out how they fit in within what is already happening in the lab in a way that moves everybody, makes all ships rise. I think that that's a great skill that he'll carry forward in his next thing. So without any further babbling from me, I'm going to turn it over to Sam. I think good rules to follow. If you have, as he's presenting, let's minimize the interruptions, but if you have clarifying questions, ask those, and then we'll open it up for questions for everybody afterwards, and then we'll ask you all to leave, and Rob and I will have some quality time with Sam after you all go. All right, so take it away.
All right, thank you, Nelly. All right, thank you all for coming out today. The basic concept of what I'm going to present today is my footwear simulation that aims to improve speed and usage within the footwear testing process. All right. So, I am frozen. All right, so a brief overview of what I'm going to discuss today. I'm going to start by discussing the testing and design process of footwear currently used today, and highlighting the lack of internal load information that we know of the foot during this process. Next, I'm going to address how current simulations are tackling this issue of determining internal loading within the foot in footwear, but also point to the slowness that these models currently have. Next, I'm going to discuss my approach using a simplified geometry. And then I'm going to start talking about how I began to apply my framework within the footwear testing cycle. All right, so why focus on running? Besides me really enjoying running, running is one of the most accessible hobbies, needing only a pair of shoes, a place to run, and the motivation to do so. Due to both its accessibility and its cardiovascular health benefits, 15% of Americans participate in a form of running. Now, people are beginning to run further and faster than before, with marathon participation exceeding levels pre-COVID and approaching their highest point ever, and marathon times being the lowest they ever have, including the marathon world record being broken just this past weekend. Interestingly, youth marathon participation has also risen from 9.2% to 12.1% from 2016 to 2020. And looking at the market size of the footwear industry, it's about 500 billion right now, and it's expected to rise near 700 billion by 2030. So a massive market size. So with this great investment by companies and also consumers, how are we ensuring that these products are meeting both our biomechanical and performance needs? This is where the testing of footwear comes in. So we don't know too much about what companies are doing. They don't release specifically how they test a certain footwear. But from bits and pieces, we know that they follow about 3 different tests. There's mechanical testing, where we learn properties of the midsole, such as energy return, stiffness of the midsole. And then there's motion capture, where it's the test where they suit up in like those black suits with the markers, and then they jog around on a treadmill and they're tracking their motion. This gets cadence and stride length, which they can compare to large data sets that companies have collected over the years and compare them to previous prototypes to see how they're performing. In addition, motion capture can be used within musculoskeletal models, which are common within footwear labs, and the most common one being OpenSim. And then there's field testing. Field testing is where athletes come in. This is when athletes test out the prototypes that the companies have developed, and they're testing performance metrics to see how well these shoes are actually performing within a training or race setting. And they measure VO2 consumption or volume oxygen consumption and blood lactate levels. Now, this process is very good at performance. You see the sub 2-hour mark within marathoning being broken not by one person, but by 2 persons this past weekend. With every iteration of footwear, you can see almost another record being broken. Yes, both in the same EVO3 Adidas shoes. So there are trends with certain companies doing better too than others, with specifically developments in their material property, getting better and better energy return. So this is great for performance, but how does this impact, or how are we learning and investigating what this is doing to our internal foot biomechanics? We see that there have been issues in the past. So Vibram in 2014 had to settle about a $4 million lawsuit for promoting their shoes as being healthier and inducing less injuries. When in turn, we find that studies are actually showing that these barefoot shoes are increasing metatarsal stress fractures, as well as Achilles tendonitis. And just this past week also, former world champion Abby Steiner is now suing Puma for injuries that she claims ended her career due to the footwear Puma was providing her. So by ignoring the internal foot mechanics, by not investigating with these testing, we are potentially overlooking detrimental changes within foot biomechanics. Now, there's a few methods that have been investigated to assess the foot-shoe interface and thus the internal foot loading. One of them is pressure insoles. So pressure insoles go beneath the insole of your foot, and as you run, it records the pressure of your foot. Now, this is great for assessing comfort, identifying hotspots, but it doesn't give you insight into loading within the foot. So anything internal within the foot, such as bone stresses and tendon loading, it gives you no insight. So I would rule that out for assessing further mechanical loading. The strongest candidate is finite element models paired with musculoskeletal models. So together, they're able to predict joint and tendon loading, as well as bone stresses and plantar pressures. So investigating them further in the current workflow, we start with motion capture. So this is what we're getting already in the labs. Motion capture is provided as an input to musculoskeletal models. These musculoskeletal models perform optimization of tendon load sharing through inverse dynamics, which produces the optimized and predicted joint and tendon loads. These joint and tendon loads are then inputted into the finite element model, which is the geometry representation of the foot. And in turn, we get out the plantar pressures and bone stresses predicted within a person. Now, this poses 2 problems within the current framework. First, with the joint and tendon loads being inputted to the finite element model, the tendon loading is not being driven by the contact that is actually being given. These musculoskeletal models have low fidelity within the foot region and simplified contact. So thus, as being an input, we are losing information on how the ground is influencing tendon loading within the foot. So I propose we can avoid this issue by changing the workflow that is currently used, by taking the motion capture data and inputting it directly into the finite element model. So removing the middleman to get our tendon loading, or to get our contact loading case. And then with our contact loading case determined through our finite element model, it's plugged back into the musculoskeletal model to back out the tendon loads. And thus tendon loads are now being determined through contact. The other issue is that finite element models are currently extremely slow. We are talking around 6 to 10 hours for just the simulation time alone. This doesn't include the model creation time, which could take hours, if not days, to make, which renders it incompatible within the current footwear testing workflow within the motion capture section, which motion capture takes about anywhere from 30 minutes to an hour to test per athlete. So this 8-hour time would always lag behind the current motion capture testing frame. So looking at why finite element models are so slow is because they're highly, highly detailed with strong fidelity of the foot. We're talking node counts on the order of hundreds of thousands. Materials being nonlinear for the soft tissue region. Bone joints are modeled as contact regions, adding further nonlinearity to the system. And we also have frictional contact between the foot and the shoe interface. All result in slow computational times. Adding on the model creation time, these models take days, weeks to run and create. So the goal throughout my study is to reduce this computational time and the required foot complexity of these finite element models so that we can use them within the footwear testing cycle. And we're going to start by creating a framework to utilize a simplified geometry that I'll discuss later on. So I hypothesized throughout my work that a reduced finite element model of the foot approximating the passive musculoskeletal system, so bones and ligaments, as a rigid multibody. And soft tissue, which I'll approximate as everything else within the foot, as a spring network. And this can model the foot-shoe interface with comparable accuracy to these highly detailed finite element models, but within a time frame compatible for the footwear testing frame. So briefly going over my choices that I'm going to implement in my model, we're going to start by looking at the bone. This is commonly modeled as an elastic solid within most models. However, this adds a high element count and a node count. So instead, I'm going to model these as rigid bodies, which rigid bodies have 1 node and 0 elements. So this greatly reduces the node count and the computational time required. Next, there's the skin. So the skin is often modeled as a hyperelastic solid. This is nonlinear and takes a long time to solve. So instead, I'm going to model this as a shell element, which reduces the node element count and also makes it easier on the solver. Next comes the soft tissue and also the foot fat pad. So the fat pad is sometimes modeled within finite element models, specifically for patients with diabetes, where this could come more into play. But I'm going to lump these into a bulk soft tissue property. And I'm going to do this through what I think was one of the best contributions to my model to improve the speed, which is an element that I created, which is called a spring network element, which is going to take this nonlinear solid element and make it into a spring. So each chunk of material is going to be modeled as a spring, which doesn't have issues with, say, we have large deformation within the foot. If we start deforming elements greatly, so an element wants to stay as a cube, that's the best. That's what the solver prefers. But as we get skewed elements, so this cube starts changing shape, it gets harder for the solver to determine what the load should be through it, and also can result in non-convergence. So I'm going to avoid that by having this spring, because the spring has 1 degree of freedom, so it'll always be able to be solved. Joints are normally modeled as bone-to-bone contact. Now, contact, like I said before, is nonlinear and can take a long time to solve. So instead of adding in all these contact elements, we are going to define these joints based on the bone geometries themselves. And so we are fully linking our rigid bodies into a linked structure that can move around. And with all these joints being created, ligaments, they provide the stability to joints. So I'm going to simplify these ligaments. The foot has about like 80 ligaments in it. So this would take a really long time to attach if we want to be super patient specific. And it's also difficult to see these ligaments on the MRI as well once we create these geometry, and I'll go into that. So instead of modeling these ligaments, I'm going to model them as their effective stiffness on the joint. The interface between the foot and the ground, I'm going to keep the same as being a frictional contact. There's no way around that one. But the shoe, I'm going to simplify. So it's common for a shoe to be attached to the foot. I'm going to model the shoe as just being the ground. So it's like you're running barefoot on a soft surface. So you're running barefoot on, say, your shoe, which is kind of weird to think about, but it's a simple framework to start with. Okay, getting into the model creation now. So geometry was taken from my participant, who was my brother, since we had his MRI scans readily available. And he is also a sub-elite marathoner, running sub 2:30 marathons. So this correlates well with studies that have already looked at marathoners in this category. So we took his MRI scans of his foot. We did segmentation and planar interpolation of these bone regions. We combined them from each of the three planes, each of the three scan planes of his MRI, so the sagittal, transverse, and frontal planes, combined them and smoothed them. And then with them all smoothed, we assembled them within the full foot geometry. Now you can see can you see my cursor? No, you cannot. So the green is going to be the skin. The skin, like I said before, is a shell. And the bones are all these multicolors. They're going to be our rigid bodies. Joints are replacing the bone-to-bone contact, and they are taken from the bone geometry and contact surfaces themselves. So a good example of this is the ankle bone. This is the talus bone. And in blue, all these blue nodes, they're going to be the joint contact surface. Now, this bone in particular is going to be modeled as a revolute joint, because you can think of this bone, at least the contact surface, as being cylindrical. So the bone is going to want to roll within its socket, okay? So that's where we're going to determine our joint center and our joint axis of rotation. We also had cylindrical joints, spherical joints, hinge joints, and fixed joints to make in total 5 different types of joints modeled within the body. So ligaments, they provide the stability to the joints. So to calibrate these joint stiffnesses, I use basic measures from the participant. Starting with arch stiffness, I treated the arch as a leaf spring. So as you can think in like a truck uses a leaf spring. So as you push down on the spring, it's going to want to flex more, okay? So it's kind of difficult to do, but you can think as it's pushing down, it's flattening itself, okay? So I took measurements before and after applying weight onto the foot and measured the deflection of the foot, and this translated to a rotational stiffness of all the joints within the foot, or all the joints within the arch of the foot. Then moving on to the ankle. The ankle was looked at in inversion and exversion, as well as dorsiflexion and planar flexion. So to determine these stiffnesses of these joints, I measured the torque required to move the foot a certain angle. This torque was divided by the degrees that it moved to get our stiffness. A similar process was done for the toes as well to get the toe stiffnesses. All right, so with the bone and the skin modeled, we have all the rest of the volume of the foot to model, which is going to be classified as a bulk soft tissue material. So bulk, with this amount of space that we have, this would require a large amount of elements and nodes, which would slow down the solver. And also I couldn't do over 70,000 nodes because I have the student software of ANSYS. So that also helps reduce the amount of nodes that I could use, which prompted me to make the model faster as well. So instead of modeling the chunk of material, which is usually modeled, as a solid element. I'm going to model this now as a spring. So I'm replacing this chunk of material with a spring. Now, the simplest way would just be to connect the spring from the bone to the skin. And this sounds good in theory, which is what I tried first. But then I realized this is very unstable. So you can think the skin is mainly in compression. So you're standing on your foot, it's in compression. You can think of a spring in compression, it's going to be unstable and want to buckle or twist on itself. So this isn't going to be very viable within the model. So the goal is now to put this spring in tension. And to do that, I'm going to offset a node from the skin surface and attach a spring to it. So this spring would now be in tension. So this node is referenced to the bone. So you can think of it as an extension of the bone that isn't actually there. So it's a reference point that's not providing anything other than force transfer. There's no contact of this point. So it's not like your bones now have all little tiny points that are contacting surfaces. It's just a reference point to tie to. And we're going to tie this reference point to the skin nodes themselves. So now as the skin deforms, it's going to put this spring in tension. So now we have the length and the stiffness of the spring to determine. And this is going to be determined through the volume of material that we are representing. So this is going to be represented as a hyperelastic material. So I applied a hyperelastic theory of squishing the solid and also shearing the solid to be able to determine what this effective spring stiffness and offset should be. Okay, so with the model fully defined, next came the boundary conditions and load inputs. So I took two inputs, which were ground reaction forces and ankle positioning, into consideration for load conditions and load cases and boundary conditions. First, ground reaction forces were determined in the vertical and horizontal directions. This was taken from literature. I didn't have access to a load plate and my brother at the same time. So we estimated ground reaction forces from a paper well cited within the footwear community with elite athletes as the participants. And this is calibrated based on body weight too. And then came ankle positioning, where we took video of my brother running and used ankle positioning and tibia position as the input into our model for boundary conditions, specifically displacements of our bones. All right, and now I have videos of running the model. So this is deformation. So blue is little deformation and red is high deformation. And we can see that the deformation is making sense. It is following what we're said, and we're not seeing any weird rotations. So if we saw weird rotations, we would have to adjust our parameters. Now, it looks kind of weird because the ground is moving, but this is because we're changing our reference plane. So let me do a quick demo here. So if we can think of our ankle being our reference plane and our racer being the ground, if we're applying a displacement at our ankle, the ground is going to need to move in order for our ankle to not move, because our ankle is said to be fixed in place and rotated. But it doesn't mean that the ground's not applying a force, because the ground can move up and apply that force onto the ankle. So that's why it's looking like this in the model. It's easier to set up within the boundary conditions, but it is not a simplification of the system. All right, with the model run and the framework to create this model determined, we are now going to verify the reduced computational time with the similar accuracy to these high fidelity models. So models took around about 8 hours to run on average. That's a comparison. My model took 10 minutes to run. So this is a 5,000% reduction in computational time. So if we're thinking that motion capture is going to take 30 minutes to run, we can now fit in this finite element testing to get internal loading of our foot, providing more insight into stress, bone stresses, and planar pressures. To assess accuracy, I'm going to look at ankle moments So this is going to be a plot of our ankle moments that I extracted from the finite element model. We can see that the peak ankle moment is occurring at mid-stance, which is making sense. And comparing this to the study that, oh my goodness. Okay, well, I don't know what happened. Oh no. Well, that was going well. Interesting.
I did. You're doing great.
Okay, let's try this again. I did. You guys didn't hear me say anything else after that. I actually went through the whole presentation. Huh. Okay. Yeah. Oh my goodness. Oh, this one. Okay, we are back, but not on the Zoom. Second. All right, I believe we are back on the Zoom. Okay, we're good on the Zoom now. So I don't know what happened there, but I'll just go back to what we were talking about before. With peak ankle moment is occurring at mid-stance as expected. Next, we are going to compare our recorded ankle moments to the experimental values. So these experimental values come from that paper that I took the ground reaction forces from. So we can see that it is slightly lower than expected. And there are some explanations for this. First, my participant was 10% lighter than the participants within the study I'm comparing to. So this could lower the moment. And also, I didn't model the stiffness of the shoe within my model. So when you're wearing a shoe, your shoe has some longitudinal bending stiffness. So it wants to resist flexing. And the degree to that flexing also depends on the shoe itself. So you can think carbon plated shoes, the reason why they're so fast is because they are increasing the longitudinal bending stiffness of the foot shoe system. So by not modeling the shoe or not attaching the shoe to the foot, we are decreasing the moment arm that would be created and also decreasing the moment that we're recording. But we still see that the shape is following as the graph is trending. So I'm going to say that the ankle reaction is most likely reasonable. Next, with the ankle moments determined, I'm going to plug this into my musculoskeletal model to perform inverse dynamics and get out the tendon loads. So we see at, I'll come over here. So we see at the, oh, this is probably real. So we see at heel strike, we see that the two calf muscles here in this blue color are going to be the soleus and the gastrocnemius are the highest loads. But then we also see this tendon here, which is the extensor hallucis longus, which is the tendon that runs along the top of your foot and goes to your toe. So it's a pretty prominent tendon, so you can see that one. But we also see that being high as well. So this makes sense with heel strike. With this tendon being experiencing a high load, this is resulting in your foot flexing upward, which is dorsiflexion. And we see as we transition through stance time, the calf muscles are doing predominantly all the work, which makes sense since these calf muscles are connected to the largest tendon within your body, which is the Achilles tendon, and providing a large amount of force to move you forward. Now, looking at a normalized tendon force plot, normalized tendon force is going to be the force that we predicted based on the amount of force that the tendon can actually produce. And we see that by far the highest one up here at 80-something% is going to be the toe tendon. So it's performing most of its work at the beginning of stance phase. And then the calf tendons also go up to about 80% during stance and propulsion. So this makes sense in that the tendons are performing at about 0 to 80% of their normalized value, because tendons, the body optimizes tendons, so they don't want to make them over-designed. So by using almost their full range, it's correlating well to how we would expect tendons to perform. And while I didn't compare it to anything else, such as plugging these values or plugging my motion capture data into OpenSim, OpenSim would also provide tendon loads. And this is a common system to use to predict tendon loads within footwear testing. So future efforts could go on to compare these tendon loads even further with this software. And one point I want to make about my model is that it handles large deformations very, very well. So with the skin being modeled as the shell element and the soft tissue being modeled as a spring element, it can deform greatly. Especially, you can see in toe off here, there is a high flexion in the toes and the skin has to wrap around it. Now, if I was modeling the soft tissue as a solid element, these elements would be highly skewed. They would get very flat, very trapezoidal, and not pair well with the solid. So by having this removal of solid elements and replacing them by springs, we're able to handle this large deformation well. So the key takeaways of this model are that it's a straightforward model creation. I use simple patient-specific geometry to create this model and tuned it with the patient parameters. In doing so, this also leaves an opportunity for this entire process to be automated. I did a lot of repetitive actions throughout this entire process, which would pair very well for using an automated system to do this, and also speed up the entire process. My model had a fast computational time, about 10%, 10 minutes, which is a 5,000% reduction in time, which would enable it to fit within the time frame of motion capture trial testing. And it predicted results with reasonable accuracy. Tendon forces operated on their 80% range, and these tendons, most importantly, are driven by contact, not by motion capture data, which is assessing low fidelity movement of the body. Okay, so now with this finite element model that I created, which can pair within the footwear testing cycle, I put it to work within the footwear testing cycle. Or at least I started to. I'm in the works of getting human protocol approved to conduct the future testing, but I did begin this process and I want to outline how this would fit into the entire sequence. So we look back at the testing of footwear that I had before. And this model would fit into the motion capture period. So as motion capture data is being collected, we are going to run the FEM with it to collect internal loading of the foot to provide even further insight into footwear and prototyping. So starting with the mechanical testing of the midsole, we printed some additively manufactured material. Additive manufacturing is becoming very present within current footwear companies, with almost all major footwear companies working on an additively manufactured shoe, with Nike coming out with theirs a couple of months ago. Puma is now working with carbon to print a new shoe. Adidas historically worked with carbon to print their shoes. So I wanted to dive into the realm of additively manufacturing shoes. So I have my samples up here too that I tested. So I wanted to get the material properties that I could input into my finite element model to assess how the footwear is working. So to characterize this material, I did a stress relaxation test, which in simplistic terms is you apply a displacement, you hold that displacement, and measure how the force responds. So I varied across a range of strains, and these strains correlated to strain rates that I would see in footwear. So across the test, these are what I see for the force outputs. They're normalized to be stress. So stress is going to be our force divided by our area. And we see that this material is highly viscoelastic, or putting it another way, force is going to be decaying with time. So we see that there's initial high peak in force, and then it decays as we hold that displacement. We also see a rate-dependent stiffening effect of this material. So simply put, this material is really nonlinear. So I'll just go back. To model this material, I applied a simple viscoelastic model to characterize this material, and it worked pretty well. So then this material model would now be inputted into the finite element model as the material property of our shoe. So next steps would be to collect this motion capture data with an additively manufactured midsole, which was the material that I characterized. I would then apply my finite element model to the motion capture data I collected to analyze how tendons are being loaded and compare this to a normal shoe, I would say, a normal marketed shoe, to see how tendons are being loaded and compare the differences in terms of biomechanical effects. And then from there, you would collect performance data to see, like, does this shoe actually help you? Since we saw a lot of viscoelasticity with the shoe, it probably would not help you that much. It would be kind of like running on a like molasses almost. You'd be losing a lot of energy through it. It would be kind of difficult, but it would still be cool to test out the finite element model to see if it can capture that. And the cool part about this is that now you can start iterating. So say we saw, oh, this shoe is terrible. It's like you lose so much energy running on it. Now you can start tuning stuff. So you say, okay, maybe I need to change this material to be more energy efficient. And so you tune it, keep going through this process. You know how it's performing in terms of like how fast you're running with it. And then you also know, is this good for my foot health? Is this going to lead to bone stress fractures, tendonitis type deals? Okay, so there's a lot more work that can be done on this model. I just built the framework for it within my short 2 years to make this. But automation's a big one for it. So the finite element model runs within ANSYS. My geometry creation runs within CAD software. My joint determination runs in MATLAB. I pull the ANSYS results from Python. So I'm using like every single piece of software that I have access to at Cornell. So this would be nice to shift it outside of all these platforms into one interface that footwear testers can use. And following the trend that OpenSim has is to make this an open source software so it can be readily available within research and footwear labs. To assess bone stresses, I would need to create a breakout model. So this is actually something that I adopted from working within the aerospace industries as a stress analyst, is we would do kind of we would call it a global model. So a very coarse model of the entire helicopter. And then we would perform detailed analysis of specific parts, taking the loads that were predicted from our coarse model and inputting those into this detailed model to get how stress would be running through the system. So the same thing can be applied with the bone. Since bone is being modeled as rigid, it has zero stress on it. It can't deform and it can't be stressed. So we would take the bone, we would take a model of a bone, apply the loads that we produced in the FEM, and we would now be able to predict bone stresses. Adding fatigue into the model, or rather translating the results of the model to correlate to how our muscles and how our tendons, muscles, and bones are being fatigued, is also critical to strengthen this model. Most results within footwear are not, or most injuries within footwear are not going to be due to a single injury. It's going to be a buildup of micro injuries to result in, say, a bone stress fracture or tendonitis. So at correlating the snapshot that we get from our finite element model to a fatigue model would be critical to predict if this footwear is actually doing detrimental harm to us. And what is a really cool area of research being investigated and applied to companies is markerless motion capture and IMUs. So IMUs are little tiny accelerometers, and markerless motion capture remove the need to have that black suit with all the dots all over you. So now you can start getting data from races, race settings, training settings. So now you can really start investigating how these shoes are performing and loading your foot and other regions within race settings. So how is the shoe actually performing outside of the lab, which may be, so if you run on a treadmill, you change your gait. And if you're trying to hit a force plate, you also change your gait. So having it in the most accurate setting would provide even further resources to apply this model. So in conclusion, what I did for my project was to create a framework that incorporated finite element models within footwear testing workflows. So I reduced it from 8 hours to about 10 minutes, which now enables it to be used. And I did this through simple model creations that were patient specific. Critically, I'm able to provide key insights into internal foot loading in response to various foot prototypes. So we can now assess and prevent detrimental foot health, detrimental harm to our feet, and to create better footwear moving forward. All right, thank you, everybody. And if you have any questions, feel free to ask. Yes.
So you mentioned a couple times that the bone model you used is rigid kind of but I noticed on the definition slide
Yes.
there were some gradients applied on bones. Are those like other features that are like a top? What exactly is going on?
Yes, so that's a good question. So this was within the model, I actually have this in a folder called fake bones. So there is an issue within ANSYS in that, yeah, I was suggested to rename them, but I did not, so. Oh, that's interesting. It does not want to display it on the board. Let me just stop sharing fully. Oh. Ever since the computer took over my slides, all my tabs have been funky. So we're getting there. We're getting there. Aha, there we go. Okay. So let me share this with Zoom now. Okay, so Zoom can now see this. So we go up to those gradients that you saw in the deformation plots. Yeah, so if we play it, you can see that there are the bones having deformation gradients across it. And that is due to nodes that are being placed on the surface. So these nodes are placed on the surface, but not constraining that rigid body. So they're following the rigid body themselves. Yeah, and so because I needed to attach the skin node to the bone node, so to do that, I had to create the nodes, which ANSYS doesn't let me mesh a solid body. So how I did it was I told it, you are contacting the ground now, even though it will never contact the ground. And that way I trick it into creating a mesh around the surface of the rigid body. But it's not slowing down the solver because I put a tolerance on it of, say, 1 millimeter. So since I placed the contact surface on this bottom of the ground, the bones are not even close to it. It's not going to recognize the contact and it's not going to slow it down.
So is it effectively like a?
Yeah, it just wraps around it. Yeah. So usually rigid bodies have one singular node at their centroid. And so it's mapping the distance to the centroid and it's moving with the centroids. Yeah.
Great job. I really like the project idea, the work, it's amazing. I have a lot of questions, but maybe I can ask you. So, related to the mesh.
Mhm.
So, since you're using a software, like student
Yes.
software. Will a time step or any other method contact, like any of these assumptions will play a role in increase computational cost or like increase the accuracy of the model? If you would increase, time step.
Yeah, so increasing time step, I found it increases it only slightly. A lot of the time is spent building the model, so building it and then solving it. And then when you actually take smaller time steps, say I used 5 time steps to apply loads, so I did 5 load steps. But when I'm interpolating between these load steps, it's actually easier for the solver to now solve, so it converges about the same speed. Because it's taking, I believe, because it's an iterative solver, it's not a direct solver. So I believe it took about like 500 iterations. So I don't expect it to take too many more iterations going along the whole process. Because it's almost like meeting the load steps along the way. So it's almost like this, almost following the same process.
So
Mhm.
So could you say again, what is it for the stiffness of that spring?
Yeah, so this is how I actually calibrated it. So I used an indenter. So I used a solid model to calibrate it in terms of what it should be. So I applied an indenter and I said, the indenter is close to how the heel bone is indenting into your soft tissue. So I'm going to use this indenter model to calibrate the stiffness of the elements. And I found this actually correlates very well to hyperelastic, what you would expect out of a hyperelastic material, since it's less affected by boundary conditions. So this normal loading was very, very affected by boundary conditions. So since it's a very thin region compared to like the plate that would be squishing it, you would end up with a lot of boundary conditions. And I found it would have to be a lot stiffer than what theory would predict it to be, of just like saying like, I'm squishing this material. So. Yeah.
Yeah, thanks so much. This was a really cool presentation. I want to make sure that I understand correctly before I ask a question. So if I understand it correctly, that all of your inverse dynamic calculations sort of like assume a healthy tissue state within the joint.
Yeah.
Would it be easy to modify this for like some sort of disease tissue state or like injury to be used for like a rehabilitative or physical application?
Yeah, so this was actually, it's inverse dynamics is a well covered topic within the models that, because I use parameters to build it. And these parameters, there's a lot of parameters that you can tune. And there's, the model I'm using is Millard, which was a 2012 study to determine these parameters. And he actually investigated how age can change these parameters. And then you can also add in viscoelasticity with tendons. So you can look at damping of the tendons. I'm only modeling it as simply a spring. So tendons are just basically just being linear elastic, but you can start adding in damping terms to start showing more viscoelasticity in the tendons over time. But I just assume since the stance phase is so quick, I can just model it simply as an elastic element. But yes, to answer your question, there are parameters that you can tune, especially if age is a big one too.
Any last final? Right. Thank you again, Sam.
Yes. Yes. All right, everybody on Zoom. See you later. Thank you for coming. I gotta figure out how to end it.
Like lunchtime.